You can learn if there are edges between sharp boundaries between one medium and another.
Right.
Occasionally, you can have a wave that reflects off of a surface. It's a very complex map that you make from all of these signals when they're done. And it's not just earthquakes. You know what else gives you these data? Underground nuclear tests.
Oh, wow.
And those are especially valuable,
Right.
geophysically, because you know exactly where the test occurred.
Right.
So there's less uncertainty in where the epicenter is.
You hear
And
that, North Korea? We're on to you.
So you add up all these data, and you can reconstruct what the center of the Earth, what the entire structure of the Earth would be like.
Wow.
Okay, without ever having gone there.
That's amazing.
Yeah, and these are basically sound waves as they go through.
Exactly.
Okay?
That's crazy.
Pressure waves. Yeah, so it's pretty cool.
That is.
So another thing.
Global warming, right?
Right. So she explains that part of it pretty well. And what she's leaving out is the part I said about the core of the Earth and the ocean and the land masses, because that gets into some fundamental stuff that's really tough. But that's the real energy, because Earth also has its own intrinsic frequency and rate that it vibrates at. And that's why it's blue and green to look at from space, and why we have a blue sky, is how all that stuff she says in the video works with the spin and differentials of our orbits and spin with the bulk of the mass. Lots of energy there.
Oh, yeah.
And when you, right. How do you talk about that and add it into the atmospheric view of climate change? In even Sabina's video, that you can go into that for months and write books about.
Oh, sure. Well, and so, okay. Here's the part that I just want to talk about a little bit about the exchange. The interesting thing that she said, and the thing that caught my attention was that the atmosphere and the temperature of Earth is seeking balance, right? There's a thing going on. You know, she talked about how warm the Earth would be if we had no atmosphere, which relates to how much energy we're receiving from the sun, right? And how much we're reflecting at a constant rate. That's what it would be without the atmosphere. It would be negative 16 Celsius, right?
Because there's nothing to hold anything above the surface where there's thermal mass. Remember our talk about thermal mass, right?
So with the atmosphere, we have there's a bit of a constant, right? A temperature that the Earth is held at, constant-ish. But
can we pause right there where you're at?
Please.
Because that's a good place to pause for added going into space and heat without the atmosphere. Notice it's cold at the surface, but the landmass underneath, right, is still the same relative temperature. Yes. Right. So where's that heat going? Nowhere. It's held underneath to the point of expansion limit that the material has to take up the space that it's allowed for in that motion. And if you add an ocean on that, and then add the gravity physics that she's not talking about, then you get an atmosphere. So to not have an atmosphere, you also not have to have an ocean.
Right.
So I'm sorry if that confused where you were.
No, not at all. But that's what I'm still, not at all, because
it's a big link is all I'm saying.
Right. And there's so yes, the core of the Earth, right, has a warmth, a heat value, right, or
a lot of it, yeah.
Right. And
if you didn't have the mantle, you wouldn't see that until you went inside the core. It would be further inward,
right,
for the same reasons.
Right. And so it would work in the same way. Adding the atmosphere and the oceans on top just creates another layer of kind of the same, I guess, transfer or balance,
Well,
maybe?
Capacitance and inertial mass with a capacitance ability to hold on to so much weight in the form of energy and heat, right? Whereas Mars doesn't have enough land mass for stuff to do that, so the water goes right to space. Whereas Earth has landmass and core to hang on to stuff gravimetrically. And we send hydrogen to space. So when we lose heat, you literally, if we're losing more red energy, we're losing more larger inertial mass in the form of hydrogen, which she's not getting into. That's a whole other ball of wax to talk about.
It's even more complicated.
Yes. that's postdoc stuff, and she's, how to do a video on that easily without a lot of math. I don't know.
Right.
But it's the same discussion. So Earth is in a unique position in the solar system, and with a unique conglomeration of mass to be able to hold oceans and air. And if you're talking about stratification of thermal mass in the air, like she's doing really well, she does that extremely well. And you have to then step off the diving board into the oceans and see how that stratification she's talking about is literally a differential between the thermal mass layering of the ocean and its relationship to the spin of the Earth.
We know from physics that moving electrical charges create magnetic fields.
Right.
Okay? Faraday first noticed this. And vice versa, okay? So you can move a charge, there's a magnetic field that's created around it. You can take a charge, move it in a magnetic field, and the magnetic field will induce a current in the wire. So Faraday did this. So he had a magnetic field, took a wire, moved the wire through the magnetic field, and an amp meter moved. A needle moved because current was introduced into the wire. That's how electricity is made today.
Exactly. Right.
That's what a turbine is. All right? You're moving wires through a magnetic field, creating a current.
Wow.
Okay. And with power plants, everything about a power plant is so that you can sit there and move wires through a magnetic field.
Anyway, it wasn't until the 1970s that Doug Vogt came out with this idea that the sun does nova. And unfortunately, by that time, interest in catastrophism was going from a raging, burning fire down to little smoldering embers. And it did not receive the respect or attention that it truly deserved. If not for Charles Hapgood, both Chan Thomas and Doug Vogt probably would have had a much more influential play over the entire world, scientific discourse, things like that, than they actually ended up having. Up next, we're going to go and we see this very wide, lighter blue line, and that actually probably should extend all the way back to the pink line. But the NSF, the National Science Foundation, hand in hand with the CIA, a lot of people don't know that, they began overwhelmingly funding studies that would come out with something contrary to the idea that this catastrophism thing was real. Basically, Charles Hapgood threw the axe, and then the National Science Foundation helped scientists little by little kick a dead horse, or a dying horse at least. But while that was going on, turns out Earth, the sun, the universe, they are snitches, and you couldn't just hide this from people who had a good brain. That's when Robert Felix, August Dunning, Randall Carlson, Robert Schoch, Anthony Peratt, one of my favorites, Paul Laviolette, Billy Yelverton, and myself started to really figure out, wait a minute, no, this story's not right. There's something else going on here. And then we have 2018, where we had the declassified document containing the Adam and Eve story from Chan Thomas. Now, I am aware that there were portions of it, including the second version, which never actually were classified and hidden in that way so overtly. But at the same time, most people didn't know about it at all. Nobody had any idea about this. Now, I know we're going to get some people in the comment section. I heard about it. I was one of those people who heard about it. Well, one, good for you. Second, the way that I see people commenting about that makes the point. You were special if you knew about it. Most people didn't. But when that came out in 2018, we got our hands on it in just a couple of months, and we ended up making that story called The Next End of the World, CIA Classified. And that video's got millions of views. That's what actually inspired Jimmy from Bright Insight to really take what he was already starting to figure out. He was, credit where it's due, but that really kind of shifted his gear and allowed him to figure out so much more. It shifted the gears of so many people, and it really was the birth of catastrophism back in 2018 there. And since that time, you know, compiling millennia of geologic evidence, compiling centuries of human research into this. Since just 2018, we have tripled the amount of information that has come out in the peer-reviewed journals, or modern observations corroborating this, or modern awareness of galactic astrophysics or plasma physics, things like that, which help corroborate and fill in all the little holes of the story. So that's your basic timeline. Now, what we have up top there is a list of some of the people, theorists, and what they think is going to happen. Now, I'll admit this chart is a couple years old. Some of these things may have been altered, may have changed in some people's minds, and if that is the case, like I said, I'm just presenting the chart that was absolutely true back in 2020.
So that's so amazing. It's such a simple concept.
It's a simple concept.
And that's just
when
been
Faraday
scaled
first-
up to this huge
Scaled
form.
up.
It's amazing.
It feeds the civilization. When Faraday first demonstrated this, and there's just a little meter, it's like, that's cute, Michael. Okay,
Right.
what's Michael been doing today?
That's
all right. There's a little meter. That's a nice toy.
Right.
And there's a famous quote, maybe apocryphal, when asked, when he asked for more funding, and he says, "Of what value is this to the British Crown and the British Empire?" And he said, "I don't know, sir, but one day you will tax it."
Wow.
That's how you make electricity. All right.
Who told them this was a good idea? Mexican private company going to spray the sky out of a high-altitude balloon this week, simulating volcanic stratospheric injection in an attempt to cool the Earth. This is atrocious, and you couldn't wait for northern winter to end, eh? Geez. In that same vein, they're discussing launching space dust from the moon to block solar radiation incident on Earth for the same general idea of cooling the planet, which is another terrible idea. It's also a bit of a nod to the dust creation of the coming solar micronova and why it helps put a rapid freeze to the planet when it does erupt. Like we don't already have enough going on without having to worry about humans trying to play God in the sky. Lastly, on the article front, good one here about the GPS disruption during the 2017 solar storm. It was the biggest of the last solar cycle. Now, while some levels of disruption were expected, this clearly exceeded what would normally have occurred during past solar cycles and events of similar magnitude, once again implying the weaker magnetic field of Earth during the ongoing pole shift is making Earth more vulnerable to lesser and lesser solar storms.
But let's get back to the Earth.
That is
So-
also how you talk to any government anywhere.
Yes. If you're a scientist and an inventor.
Yes.
So you have this liquid layer. If you have a liquid layer, then the iron can move within that liquid, and iron is an electrical conductor, as we've known since childhood, with the iron filings on the
magnets.
on the magnets,
On the sheet of paper.
Okay.
Yeah.
So when you have these electrons provided by the iron moving, it creates a magnetic field, and that is the origin of Earth's magnetic field.
There you go.
That's the origin.
That's super cool.
Okay, and it's something called a dynamo phenomenon, where you have this circulation and this continues. And by the way, as is true for the sun and in many astrophysical objects, the dynamo runs a course of life where it gets stronger, then it gets weaker, and then it gets stronger again, but with the opposite polarity.
No, I'm like a phoenix, baby.
Oh, so we have evidence from iron that has been spewed forth from volcanoes that then solidified in place, capturing the magnetic field at the time that the field was laid, and we see evidence every several 100,000 years of the magnetic field of Earth flipping.
Pressade priser på Lidl. Minst 40% rabatt på apelsin. Storpack färsk blandfärs.
Back and forth.
Look at that.
So that's on a cycle, okay? The sun's magnetic field flips on an 11-year cycle. Okay, sun has an 11-year cycle, and every 11 years it gets more luminosity and less luminosity. But every 11 years it'll do the same thing, but with the poles reversed. Okay. Okay, so now let's get back to this. The core basically rotates with the surface of the Earth, but occasionally will rotate a little faster,
Alrighty.
slow down, stop, and then a little slower.
Okay.
All right, so we're all comparing it relative to we on the surface. And the recent measurements showed that the solid core of the Earth was trailing behind Earth's surface.
Earth, wait up!
I know, right? So presumably, this has always been happening. It's not like there's something new, but there's a periodicity of this that they're estimating to be about 70 years, where it'll slow down, catch up again, overtake us, slow, and then return. So these measurements are affirmations that the core has its own sort of rhythms inside the liquid iron within the rest of the Earth that's rotating around it.
All I know is this whole thing was worth it just to hear the word periodicity. That, I mean, I don't know where you pulled that one from.
We use that word all the time.
Oh
That's
my
right.
God,
Yeah,
period.
the rhythms of the universe, to find them, we track their periodicity.
Ooh, look at that. Let me tell you something. If you gave that to like, you know, the people like Always and Stay Free and all, they would love you because that's a beautiful word.
Oh, what?
I'm telling you right now. You will.
You're talking about feminine products
Yes,
on television
I'm saying,
ads?
like, you
That's
know,
what you're talking about?
There's so much like stigma unnecessarily
and
attached
euphemistic
to those.
terms. Yeah,
and
yeah.
right. But instead, it's just like, hi, yes, I'm going to need some periodicity products. Thank you. And I'm totally cool with that.
Okay, all right, thank you,
Mom,
Jack.
send me to the store to get your periodicity stuff.
Okay. All right, so anyway, so we're still trying to figure out what it means that we have this 70-year cycle in the center of the Earth. But right now, Earth's magnetic field is weakening.
Okay.
But it's not going to go away in anybody's lifetime, so nothing, I wouldn't worry about it.
Right.
And by the way, there's no evidence of extinction when the magnetic field went to zero
When
and
it
then went
flips.
back up.
Right.
When it flips. There's no. So because people say, well, the magnetic field's protecting us from the dangerous rays of the sun.
Right.
And maybe, but whatever damage it caused, it's not even a blip in the fossil record. So, and the fish don't care.
Right.
The fish are underwater. The particles don't hit them ever. Right. So they don't care.
Everybody's fine except Harold. He was in the wrong place at the wrong time. Harold, we're sorry.
Harold is the fish. What? That is totally a fish name. How did you get the clueless fish named Harold? That is so the name of the clueless
Who got
fish.
fried when the poles flipped.
That's what you get for trying to use those legs. That you should have stayed in the ocean.
Stay in the ocean, Harold.
She was saying at pre-industrial levels of carbon, we were already at the peak stasis point of pushing energy out into space, right? In order to balance. Like we weren't, and so when you said the oceans had to absorb enough heat in order to actually start creating, right? They're pushing the atmospheric, they're driving the rise in the atmospheric heat, right? Is that because the
Right.
oceans have stopped being able to absorb all the heat?
Correct.
Right.
Or at least they have certainly slowed down their absorption, their capacitance capability for it. Yes.
Right. So they were the sponge that was soaking up the excess heat, right? And for a long time, or and then
Since fire and sticks. Yeah.
right. So they've been absorbing all the excess heat, and now they've absorbed too much heat, and they can't absorb anymore. And now it's up. Now the atmosphere is like, well, I guess I'll take on the heat, right? So, so yeah, she was saying in the atmosphere that is also happening because prior to our adding, 100 and whatever it is more parts per million of carbon we were already at capacitance in the atmosphere as far as pushing heat out into space. And so when we added more heat, that actually, now we were already we were already at an imbalance 200 years ago, is what she was saying. And now we've put more, now there's more heat, and now it's like, now we're really at an imbalance.
So all those high school physics people out there and beyond, and anybody that does cooking, what happens under those conditions? You think of the Earth as having a lid because of gravimetrics, right? Mm. You keep adding heat and stuff, you get pressure, and that's what holds the stuff into the ocean. So when you shut down, I'm bringing in masking to the discussion, since that's going to be what's in the comments anyway. Right. If you bring in more stuff and more heat and more pressure, once you stop bringing in more stuff, right, and you have the same amount of heat coming in from the sun, you have the same amount of energy from the oceans basically in spin, the atmosphere all of a sudden is not going to have the mass coming in that pumps the heat into the oceans with pressure. So you have, boom, a higher temperature in the atmosphere because the oceans are able to push stuff out into the atmosphere, or energetic things, easier. That's what happens. It's not like they're.
You're gonna have to explain that one again to me, because that one that you lost me a little bit on that one.
Okay. So I'm not.
How does the lack of dimming?
So it's like a heat pump, right? If you have a heat pump and you have the right kind of stuff in the heat pump, and you add pressure with the piston on one side, what you're doing is squeezing out the energy, the ability to wiggle for the stuff you've got. Mm-hmm. And where does that energy, we see that as a transmission of heat to the material, the copper around it, that is pressurized in, given the medium around the copper moves enough to take that energy, those wiggles, and move it somewhere. Right? Well, the Earth is doing the same thing. And the more we load energy in the form of thermal mass in the oceans, it's like a spring. And to keep that spring loaded, you have to keep pushing on it at least the same rate that you've got it pressed under to begin with. Once you end or reduce that pressure.
And that is the dimming part of it? Is that what you're saying? The sulfates and the...
Exactly. It's able to take that material largely around the ice formations on the water at the poles and on the land masses, and condense that into heat, into the most capacitance available to it, which is mountains and ice and oceans and ice. And it's very difficult to measure that. I'm sure they can track some of it and have. But you get a large exchange of masses where the ocean takes up the mass, not just energy, but actual mass, like the heat pump does. And then on the other side of the heat pump, you've got now a big expansion happening, right?
Yeah.
Because you've got cold Freon or whatever you're using, and the atmosphere is the same way. Once it hits that ice, once it hits the stratosphere, rather, it's able to expand and absorb a lot of heat. You see cooling.
Right.
What do we see going into space? That's a real complicated explanation. There is a video on the outline that I've put up having to do with abiogenesis at the core. Dr. What is his name? Eric. I'm sorry. I'll email you that video and his name. Okay. He explains the process where hydrogen goes into space really quite well.
Okay.
And that's what we're talking about here overall. And that's left out of most of the climate models also. I don't know why. But you're seeing that as a red shift also. When you see bigger thermal mass go out, the thermal mass of a molecule is not like a photon, right?
Okay.
You've got different inertia states. So you see a color shift.
Okay.
And I don't know if that answers your question or makes your question worse.
I mean, on some levels it does. I understand this as a layman. I'm not a,
That's how I'm trying to explain it, but I'm having difficulty myself with doing
I mean, I get the basic gist of what you're saying. So, you know, but for me to actually turn around and explain it to somebody else, I would be like, I'd have a little bit of a difficulty in that. So,
well, how about
that's why I wanted to have you come on and explain it, you know, better than I could, right?
I hope, but I don't know if that's true. Understanding
well, it's still also
two completely different things.
on a basic communication level, this is why, you know, I can see people who don't understand climate science or don't believe in climate science or are skeptical of it watching this video and just going, this is just a bunch of gobbledygook to me, right? Because it's theoretical and it's hard to understand, you know.
Well, theoretical, that's a big word, isn't it?
It is. But you know, for some people, understanding all this is like, you have theoretical, meaning you have to understand the theories behind what they're explaining, right? You have to understand like how everything works, right?
Well, let me apply this then. So if we send a rocket to space, right, we have so much mass and we need so much energy to produce thrust that cancels the mass's effect of gravity, right? The effect of gravity on that mass.
Yep.
Well, what most people don't know is it's not the rocket going up that does that. It's the rocket's velocity horizontal to the direction of the Earth's spin. And we're basically just wanting the rocket to be able to stay aloft long enough to allow the Earth to spin away from where it falls.
Got it.
Okay? And the same thing goes with everything up there. All the molecules of our atmosphere, and you and me too. Only we're in an inertial state where our distance from that, just you can't even talk about that with going into some fundamental theoretical physics.
Right.
With the rocket, we can talk about it without fundamental skill, right? Without fundamental physics.
Sure.
It's just a matter of scale. So the same theories are keeping the rocket and satellites up in space that we're talking about now. It's just a much different scale.
Sure.
Does that help?
Yeah, I think that helps. For sure.
Okay.
For sure.
What do your chatters think?
Well, somebody is asking, so this speaker doesn't believe any light can be reflected back into space, like marine cloud brightening, mirrors, gold reflecting surfaces to cool anything? What do you think?
Not to cool
or
anything.
Increasing albedo? Would that help?
Right. See, that's where albedo. So let's talk about albedo. So if you have and you can look this up on some of Yi Tao's argument as well, and he's big on reflecting energy. Mm-hmm. He'll tell you in his writings or his talks that the albedo of a solar panel is such that the heat trapped by the solar panel day in and day out is much greater than any effect you might have in saving from producing electricity from it without looking at anything else. And even that's a great oversimplification, because in a condensed matter way of talking about it, I could say you can bury the panel, 5 feet underground, and the inertial drag of the panel is going to change the nature of everything we've talked about and add every single cycle, day and year, more energy to the system, etc.
Yeah.
Along with the incoming energy of the sun, because what we're assuming here is that the incoming energy of the sun remains constant. At a subatomic level, it doesn't.
Right.
In a Newtonian way, it does.
Right.
So that's our assumption in her video, is that that's always constant.
That there's fluctuations, but there's a constant-ish, right?
Yes, we change that every time we change the inertial stability or harmonics of the Earth, which is how you started your what you were just saying.
Right. So, well, let's get into the part where another part that was interesting to me. So, okay, so it's the atmosphere, or the entirety of the planet is seeking some kind of balance, like a thermal balance, right? And it's the energy that it holds, right? And the atmosphere is holding a particular amount of energy, right? And creating, creating the temperature at which we have a stable climate, right? Or the climate that we know now. Right?
In relation to the land and oceans, yes.
Right. So she talks about the layers of the atmosphere and how they hold on to heat and also emit heat out into space. And there was a guy, to get into it, yesterday I mentioned there was a guy that used to be on my show all the time, on the chat, not on the show. But he would say, global warming isn't a thing to worry about, because the more energy we take in, or the more heat that happens on the planet, we will eventually emit more heat in order to seek the balance. Like, he kind of had the idea that she was talking about on some levels correct, but he was missing some of the parts of it. So.
And those parts are just a world of difference.
Right.
So, right. So,
yeah.
So yeah, does heat go to space? Not from a specific physics standpoint. Radiation goes to space.
Right.
But frequency shifting is happening from blue to red in what we're radiating to space. So ultimately, we are hanging on to more and more momentum in the atmosphere and oceans. And you see that in the thermal layering of mass, which Jim Massa, again, does lots of videos about. From an ocean scientist's perspective, hearing atmospheric discussions must be extremely frustrating for these same reasons.
Sure.
Because none of that happens in the atmosphere without preloading the oceans with a lot of stuff. And so 700,000 years of talk in each atmospheric discussion, because the atmosphere is a much shorter talk. You know, the time frame of reaction and of observation in the atmosphere much shorter than the ocean.
Yes. And the oceans are much better at holding on to that energy than the atmosphere is, right?
Infinitely, almost.
Right.
Yes.
Yeah, the oceans are really holding on to that energy. And then, so
really
if you leave the oceans out of the equation, that's a big part you're leaving out.
That's the panic in my voice every time we talk. Yeah, it's like
right.
It's like a big spring that you're winding down with the rotation of the moon and the earth and the core, and no one's even got it in the discussion openly. And yet I know behind the scenes people that have to be talking about this till they're crying.
Of course, sure,
right.
But to get back to you were talking about the different types of emission, but it is an interesting part of the process that the upper atmosphere and the stratosphere are helping to kind of try to balance the energy or heat energy or whatever you want to call it by emitting more. So it would work in the same way, adding the atmosphere and the oceans on top just creates another layer of kind of the same I guess transfer or balance,
Well,
maybe
capacitance and inertial mass with a capacitance ability to hold on to so much weight in the form of energy and heat, right? Whereas Mars doesn't have enough land mass for stuff to do that, so the water goes right to space. Whereas Earth has enough land mass and core to hang on to stuff gravimetrically, and we send hydrogen to space. So when we lose heat, if we're losing more red energy, we're losing more larger inertial mass in the form of hydrogen, which she's not getting into. That's a whole other ball of wax to talk about.
It's even more complicated.
Yes. That's postdoc stuff, and she's how to do a video on that easily without a lot of math. I don't know.
Right.
But it's the same discussion. So Earth is in a unique position in the solar system, and with a unique conglomeration of mass to be able to hold oceans and air. And if you're talking about stratification of thermal mass in the air, like she's doing really well, she does that extremely well. And you have to then step off the diving board into the oceans and see how that stratification she's talking about is literally a differential between the thermal mass layering of the ocean and its relationship to the spin of the Earth, etc.
Yeah.
Along with the incoming energy of the sun, because what we're assuming here is that the incoming energy of the sun remains constant. At a subatomic level, it doesn't.
Right.
In a Newtonian way, it does.
Right.
So that's our assumption in her video, is that that's always constant.
There's fluctuations, but there's a a constant ish, right?
Yes, we change that every time we change the inertial stability or harmonics of the Earth, which is how you started your what you were just saying.
Right. So, well, let's get into the part where another part that was interesting to me. So, okay, so it's the atmosphere, or the entirety of the planet is seeking some kind of balance, like a thermal balance, right? And it's what the energy that it holds, right? And the atmosphere is holding a particular amount of energy, right? And creating, creating the temperature at which we have a stable climate, right? Or the climate that we know now. Right?
In relation to the land and oceans, yes.
Right. So she talks about the layers of the atmosphere and how they hold on to heat and also emit heat out into space. And there was a guy, to get into it, yesterday I mentioned there was a guy that used to be on my show all the time, on the chat, not on the show. But he would say, global warming isn't a thing to worry about, because the more energy we take in, or the more heat that happens on the planet, we will eventually emit more heat in order to seek the balance. Like, he kind of had the idea that she was talking about on some levels correct, but he was missing some of the parts of it. So.
And those parts are just a world of difference.
Right.
So does heat go to space? Not from a specific physics standpoint. Radiation goes to space.
Right.
But frequency shifting is happening from blue to red in what we're radiating to space. So ultimately, we are hanging on to more and more momentum in the atmosphere and oceans. And you see that in the thermal layering of maps, which Jim Massa, again, does lots of videos about. From an ocean scientist's perspective, hearing atmospheric discussions must be extremely frustrating for these same reasons.
Sure.
Because none of that happens in the atmosphere without preloading the oceans with a lot of stuff. And so we're missing 700,000 years of talk in each atmospheric discussion, because the atmosphere is a much shorter talk. The time frame of reaction and of observation in the atmosphere much shorter than the oceans.
Yes. And the oceans are much better at holding on to that energy than the atmosphere is, right?
Infinitely, almost.
Right.
Yes.
Yeah, the oceans are really holding on to that energy. And then, so
really,
if you leave the oceans out of the equation, that's a big part you're leaving out.
That's the panic in my voice every time we talk. Yeah, it's like It's like a big spring that you're winding down with the rotation of the moon and the Earth and the core, and no one's even got it in the discussion openly. And yet I know behind the scenes, people that have to be talking about this till they're crying.
Of course, sure,
right.
But to get back to you were talking about the different types of emission, but it is an interesting part of the process that the upper atmosphere and the stratosphere are helping to kind of try to balance the energy, or heat energy, or whatever you want to call it, by emitting more into space, more energy into space, right?
More red energy, right?
Okay. Right.
So for red, if you shine a flashlight up, right? Let's take away all the air so it's less confusing. If you shine a flashlight upward, if you start off with blue light, that blue light changes to red because the energy of the batteries in the flashlight don't have the amps, the current, to keep pushing that dense amount of energy up. So you've got wiggles in blue. For every centimeter you travel, there's way more wiggles in blue light than red light. Right. So if you look at Earth as emitting the same overall energy, but it's got a much higher volume of amplitude of red than it used to, it's got less amplitude of blue going out.
Okay. Got it.
So it's a really complicated discussion.
Sure.
Are you losing heat overall? No, you're heating up overall for the flashlight reason. And I don't know that that's an easy discussion even with some scientists to have. It would take some time sitting down and going over stuff. because of all the specific specialization that's happened in sciences. This is something I had to learn. I mean, and think about.
Okay.
I'm not an atmospheric scientist. The only research officially that I was involved in physics was condensed matter, which gives me a unique perspective on this kind of stuff. But my experience is not something generally lent to this kind of stuff.
Right. Got it. Well, and then another point I wanted to talk about is towards the end of the video, they talked about why global warming is caused by us, and it's because the stratosphere is cooling. And that was that was something that kind of went by me the first time, a little bit. But so if we were receiving more, if heating was due to the sun, the stratosphere would be heating, and the atmosphere, the lower atmosphere would be heating too.
There you go. That's the important thing, is
right.
the constant rate of income.
So the reason why the sun thing doesn't work is because the stratosphere is actually cooling.
Yes, we're adding mass, like a heat pump, to the system, which gives it the spin, the ability to force more energy into the oceans and land than previously.
Yeah.
To a point, and then you start heating up the atmosphere after you start hitting points where it can't take it at the same rate.
Right.
That's what she's talking about.
Mm-hmm. Yeah, so that was a key point in the video. Like, this is why the sun, it's not the sun. This is why it's not the sun, because if it was the sun, the stratosphere would be heating as well. And then something you just said just jogged my memory a little bit about that. Oh dang, what was it? I had something I wanted
to stuff. You can't just have a particle up there that gets struck by sun and it doesn't affect the rest of the atmosphere. The force of the particle or photon hitting whatever you're reflecting from is still going to push on everything around it. And that's part of subatomic physics that often is left out of most discussions because there's no easy way to talk about it. Mostly.
Right.
So, no, yes, no.
Right. Well, and then we get into the fact that the system that we're talking about is gigantic, right? And the things that are the interplay of all the parts is so complicated and gigantic, right? It's hard to know what. I mean, even in climate science, I think that right? Scientists don't necessarily they understand the basic premise of what's going on, even on on a convoluted level that she or maybe even you are explaining to people. But we still don't understand like how the seeking balance part, or that we don't really understand. There's positive feedback loops, right? And there are negative feedback loops too, and we don't necessarily understand how all of it really works. Would that be a true statement?
In a way, yes and no. You can't predict what's going to happen. You can certainly understand the limiting first principles physics and where they match both from the fundamental level to the Newtonian level. And you can go, these are unquestionable things. What's going to happen on the way to the next change of state where it's imbalance? Right. That's what you're saying. And no, at some point, there has to be a switchover where you don't have a changing rate of exchange between the zones she's talking about, because we have a constant income from the sun and a constant gravimetric relationship to the solar system. Where does that happen? Anywhere it does is not good for life, because like a boiling kettle, it's like, at what point does the rate of steam going out match the rate of microwaves coming in at a constant level and rate?
Right.
That's what we're talking about.
Right.
And if we haven't reached it yet, well, we better put on the brakes somehow, because it's going to be from simmer to boil in a higher and higher zone, which means her level of cooling is going to expand outward, or our level of mass is going to be under more pressure inward. And probably it's a combination of both. That's what you're really asking, and then the physics gets crazy and you need supercomputers to tell you what you want to really know. Because what we want to know is dates, times, and which system's going to grab us first. And no, I don't know that.
Right. And it's, you know, in an even more simplified way, like I think we can all see the trend line where the thing is going, right? The trend line on the graph is going this in a certain direction, and there's no indication that it's going to just go straight back down, back to normal, you know, right, back to where it was 200 years ago.
No way.
There's no indication of that. And
no way.
We may get a pause, right, or we may get pauses along the way. We may get, you know, reprieves, I guess, you know, because of a negative feedback here or there, right?
Not globally, but regionally, yes.
Yeah. Well, there's a good explanation from what's her name? Again, I always forget her name. Professor from Massachusetts who explains why the ice cap in the Arctic hasn't melted yet, and because of a negative feedback.
Well, on one side, on the other side, it's accelerated greatly, and from underneath, it's accelerated exponentially. And again, she doesn't talk about a lot of the stratification in the oceans, and she doesn't talk about increasing pressure, which is causing Swiss cheesing in the entire Arctic,
right,
from underneath. And I don't see that in any of her writings or talks.
Right.
I know who you're talking about.
Yeah, but she was just giving a very simple explanation, or what they thought was happening, why it had, because by all accounts, it probably should be gone by now. Right?
In certain ways, yes, and in certain ways, no. It just, again, depends on how much the ocean can take up. Mm-hmm. And then you've got, you know, there's so much complexity for someone to say definitively of why that's happened. I'm not going to go out on that limb, but I will say that we have affected the patterns of all of our movements, even planetarily. So to know the answer definitively gets into a quagmire. And I think people that make overt statements like, well, we've had a pause here, without including what I said in that discussion, and I'm sure I could add more if I worked on it, because I'm new to this game as well as far as the climate. This is just the last 10 years of my experience. And I keep adding more and more, and I keep watching people. Some of them are adding less and less, and some of them are adding more and more, and a lot of them stop right here and draw a line. Like, right. No, you can talk about how the moon changes its rate of rotation back and forth involved in what we're talking about right now. That's a lot of energy. And to say that this pause is a pause that is a good thing in any way, I think you're seeing orbital shifts that are just the opposite of that. And this is just a side effect. And that side of the glacier she's talking about, of Antarctica, that's really overshadowed by the losses overall, right, by a long ways. We can talk about individual bodies of ocean that are cooling as well, here and there.
Sure.
And it's the same thing. You're just seeing a greater capacitance for stratification. When it's the lone wolf that's experiencing that, that means the next time around it accelerates way faster, generally speaking.
Right. Well, and it's the same with the polar vortex thing that's happening, right? Where
exactly
you're getting all of a sudden it's colder than it's ever been, right? Or it's just colder than usual a lot in a place that's usually kind of warm. It's like, well, that doesn't, that's super regional. That's super very, that's like a extremely localized effect of something that's happening planetarily. That if you didn't understand what's happening planetarily, well, then of course you're going to be like, "Where's that global warming? Thought we were having global warming." It was like, well, yeah, in the Arctic, it's 100 and if you wanted to compare how hot it is in the Arctic to where it should be, the Arctic is 150 degrees right now, right? Like you're experiencing colder than usual temperatures, but in the Arctic, it's comparatively, right, from where it's supposed to be, it's effing hot, right? Like if the temperature anomalies is what I'm trying to say. Right?
Exactly.
Like if you were going to have a 6C temperature anomaly, in the place where you lived, let's say in the spring or the summer, it would be
cook.
like, it would be 150 degrees, right? So it would be like, oh, this is fucked up. This is really fucked up. Well, yeah, that's what the Arctic is experiencing right now.
There you go.
Yeah.
So if you want to, the easiest way for anybody to really see this is the Earth turning more red from looking at it, or more blue? Because more blue, it's taking in more microwave energy and able to balance with that. Less blue, it's doing that less. Mm-hmm. So it's overall heating. To argue about which points are colder and which side of the glacier is hanging on and which side's going faster, that's like sitting on a cornflake in a boiling kettle of water going, well, that side looks like it's got bigger bubbles. This side's safe still. Right. I think it's insane, personally. But I wanna bridge the gap somehow.
Right. Well, I don't think she was. Yeah, I mean, I think people are just trying to explain like why, and on any level is I think it's trying to explain why something hasn't happened yet, right? When we all thought it was going to happen earlier, right? So it's just a matter of like, well, hasn't happened yet. That doesn't mean it's not going to happen.